Okay, let's start the session today. Oops. Yeah, so let's say um, yes, I wanted to say here. Maybe I forgot to add that comment that if you want to make it, sometimes it's a continuous distribution. Okay, it's a uniform continuous distribution. So if you want to approximate by a model like that, probably you will have to make quite a lot of nodes. Okay, to approximate it properly. While this one you make really discrete sections. So in that case, it's you can use actually each section. You can model it separately. One more thing here was on the Brinkman equation that I didn't remember yesterday, so I put it here. It's basically the viscosity of the continuous phase multiplied by the alpha, okay, the volume fraction of that phase, to the power of minus zero point 0.5. The problem with that expression is that you cannot tune it to data. Okay, after you have that measurement and you measure the volume fraction, then you cannot tune it. So this expression is a bit more general in the sense that if you have measured data, then you can just change the coefficient until you represent the curve. Okay, but be careful, when you make this test in Beaker, and you make these measurements, you have to be sure that the mixing or the shear that the fluid experiences is the same that it will experience when being transported in the pipe. If you use too much, then sometimes you get a completely different behavior than if you use, the right amount. So we are going to continue today with our discussion on electric submersible pump. Exactly the same. Now we have to bridge um, the difference between the available and the required, basically the IPR and the TPR, and we say, well, what is feasible? Okay, what number can I use there? A big number? Can I use there a big rate or not? So we want to get some indication how the pump operates. And I told you there are three parts. You have the pump, which is basically, yeah, I left it. So basically, you have a lot of these things stacked one on top of the other, and they are rotating. The fluid enters into the ring and then is trying to go through these passages and then is discharged out. And then you have to send it to the other stage again, so you have to be redirected through a diffuser where you recover pressure and until you go through the next stage. The part which is rotating is here. I should have used another color, but okay. And the performance, I told you, it looks like, it's not exactly like an IPR, but it looks like an IPR. It has this shape, okay? Of course, some ESP pumps also have kind of a maximum and then go down, but that's how it looks like, such that if you think about it, you are high pressure but low rate, or wait, hope nobody's hacking the computer. And then you have um, a high rate or low head. Okay, because energy is the combination of both. So you have the same energy, you can have either one big, the other small, or the other small, the other big, or something in between. Also, I draw the efficiency. Please, correct it on your notes if you are taking notes, that I made it, just above that rate, but actually you cannot have efficiency, above that rate. It has to be bounded by the same rate of the pump. I also told you that that's for one stage. That's how it behaves from here to here. Okay, but if you have multiple stages, then you just use a multiplier. Okay, by that number of stage, and usually you have a loss factor due to that circulation of the fluid going back and forth. Okay, what is called the pancake factor. And now that's how we are going to resume today. Okay, and actually, so today's okay. And actually, we don't plot the performance of the pump just like in the compressor. You don't use delta P. Okay, you use something else, and you use a term called head. Okay, called delta H, and that's nothing more than the delta P divided by the density times the gravitational acceleration. Okay, and that's very important because it doesn't change. So you have exactly the same plot, delta H versus rate, and this rate, remember, that's the rate at P suction and T suction. Okay, that's just like in a compressor, that's the local rate, and it does exactly like that. Hmm? Now we do it like that because the head won't change if you have a different fluid with another density. If you have oil, if you have water, if you have more water than oil, if you have more oil than water, it won't change because of the density. Okay, the curve will be exactly the same. If you want to find the delta P, however, okay, initially let's say you had pure oil. Okay, let's say that you're operating here, right? If you had pure oil, the density of the oil is something maybe around 790. Okay, and the delta P will be the delta H at that point times 790. Okay, but if you have pure water, then you have the density, let's say, might be something between 24, 10, 24. Okay, and the delta P with water then will be, if you're operating exactly at the same point, will be delta H times 1024. Okay, so it's the delta P is going to be different, okay, but the curve will remain the same in terms of the head, okay, the pump head. Um, yeah, actually these curves, they are made for water, okay, you don't make it for any fluid, but they are measured for water. Viscosity does have an effect, but we are going to see that right away. I just want to wait a bit on that. But another thing that you have to be aware of is that ESPs, to control the rate, okay? Because if you say, well, if I have that case, right? Where was it? Here. Okay, and now I want to use another rate. I want to lower the rate for some reason of that well. Okay, I'm bound. Here it will say from the curve, for example, you will need a lower rate and a lower delta P, right? But if you use this pump, if you lower the rate, you're going to get a higher delta P. Hmm? So to control rate in ESPs, you can change the rotational velocity of the impeller. Okay, to control the performance of the ESP, okay, one can modify or can vary the rotational speed of the pump, okay, of the impeller. That's what is rotating, right? That is the, and the way it looks like when you increase the frequency. Okay, we don't measure it in revolutions per minute, but we measure it in frequency. Okay, and that's hertz, and the normal range is something between 30 hertz all the way to 70, and that's around, I think, 3600 rpm. Okay, if I'm not mistaken, well, a bit higher, I think, for 70. Okay, so if you increase, then you will have another curve. Okay, that will be for F1, F2, and F3, where F1 is greater than F2 and is greater than F3. Okay, and that's the way that you can regulate a bit better how much your pump is going to give. And you have, so there you have an F max, okay, F1, and then you have an F min, that they, in a way, they give you the envelope. You can reach, you can operate in this region here. Okay. The way you do it, it's you have to have a unit, a very big unit that is on the surface, and that takes, if we're talking about offshore, it takes a lot of space. You take the electricity from the tower, or you can have also a diesel generator. You have a transformer that takes it down to the to the voltage of the pump. Okay, and then you have a drive which is called the variable speed drive, where I'm able to change the frequency, modify the frequency of that current that is going to the pump. Okay, and that's where I can change from 30 to 70, and that's relatively big unit. Okay, it can be a quite a big unit, maybe here to the middle, and maybe on that, like this square here. Yeah, for one pump. And here you just have some other things if you want to control it. That was for a field in in a very remote location that the operator didn't go to the field and change it manually, so you had some communication interface such that you can change, input the frequency here, and it will change automatically on the well. Okay, with a variable speed drive. That's also what we make on the with the compressor. Then I just want to, so remember here you have a cable going inside. So you have, remember that we have this tubing hanger. Okay. You see that's at the wellhead. But then you have this part, which I always draw it, we make a very simplistic drawing at the top. You have your surface production casing, then you have your tubing. Okay, then you have this thing, which is supposed to be the hanger, and also the seal that avoids that any fluid from here will go outside. Here you have your pump, but then you have to make here a hole. I'm going to make it in blue. Okay, to make a line that will have, it will have the power to power the pump. It will have, you have some pressure sensors, temperature sensors on the pump that you have to put in all of these wire coming inside. And that might be a limitation depending on how many other things you have in your well to have space for that. Okay, so that's power, transducer, P and T transducer. Yes. So the way we make it, and that's the way I have done it in this exercise, is I say, well, the delta H is typically represented by a polynomial equation. Okay, just a q to the 4, and the order depends on the shape of the curve. Okay, sometimes with a number 3 or number 2 is enough, but sometimes you need to go all the way to 4 and 5 to actually match or reproduce exactly the curve. Okay, so here I'm going to put just an order 4. Okay, just like that. And what I do is initially, that's what I have done also in the exercise that is already made for you. You have the collection of points measured that don't always look so nice. Okay, and then you say, well, initially with the values I have, maybe it gives me like that. So I try that the difference between these two to minimize for all of them using the solver, right? Like you already know how to make. And you change all of these coefficients until you exactly reproduce the curve. Or you use a trend line. This curve is usually, manufacturers measure for a reference fluid, okay, which is typically water, and they measure at a reference frequency, okay, which is typically 60 hertz. So how do we compute for all the other frequencies, or if they don't really do the measurement, how do we compute for all the other frequencies? So we have this similarity laws that says, well, delta H at a frequency, okay, and a frequency 1, divided by delta H at the frequency 2 is just the ratio between frequency 1 divided by frequency 2 to the power of 2. Okay, that means that if I have one of them will be the reference, right? Let's say that this is the reference, and you have the value for 60, okay, and you want to know now the value for 30 or something else, then you just clear. You have this one will be 30, this one will be 60. This is the value that I measured, and that will give you the other, right? So that will be just equivalent to say delta H at another frequency will be this expression that I have here, multiplied by f divided by f reference to the power of 2. But that's not the only thing. We also have to scale the rate. With the rate, we say Q1 Q reference will be equal to F1 divided by F reference. Okay, and this equation is taking the reference rate, so we have to say the reference rate will be the rate that I have times F ref divided by F1. Okay, and then I substitute that into this equation, and then I finally get like a general expression um, for the performance of the ESP with different for another frequency. So here I have A, and this will be Q1 times ref by F1. That's to the 4 plus B Q1 F ref F1 3 plus C. You know, it's good that I chose only fourth. If I would choose 5 or 6, we will be here a while. Okay, so that's actually that's the equation I'm using. You're not going to use it right away, but just that you know how it came. Okay, I have a pump, and then to find for the other frequencies, you just scale it up and down, and that gives you basically this region here. Yeah. Now we talk about, there are also some other restrictions to that domain, okay, that you have to be aware of that. So one of them, if you remember how the efficiency curve looked like, so let's say other operational, just like in the compressor, operational constraints, we have, has to be inside the map, that point, okay? And I have other things that I have to consider, other operational constraints, okay? One of them is the efficiency. If you remember how the efficiency looked like that, but the efficiency actually looks something like this. Sorry, Q delta H, that's delta H, and that's the efficiency. Okay, so we usually want to operate within a range from this best efficiency point. Okay, we want to operate up to this level and up to another level. Otherwise, here the losses become too big. I start getting, the temperature starts to increase too much, and it's really not very efficient, the pumping process. And that's because I think I have a nice figure a bit how to a bit. I think that's very nice. That was from a conference, and actually these are measured values. Okay. And exactly the passage that I showed you before. The blades, they are designed. Okay, this angle that you have here, they are designed for a flow. Okay, for a given flow that you have. When I go above that flow or below that flow, like in that case, I'm going. The flow should be ideally like that. That's how I design. Okay, but if the flow starts to be less, okay, then the angle or the velocity with which I'm entering that passage is not anymore here, but it will be like that because you have a lower velocity. So in that case, you create. It doesn't follow exactly the passage or perfectly the passage that you have, but you will have some detachment of flow and you will have some formation of eddies. Okay, and that's what happens when you operate, outside the best efficiency. And that, of course, becomes worse and worse. At the end here, you see you have like a big pocket of recirculation of eddies that really they reduce dramatically the passage of your plane. Okay, so that's one thing to consider, the reduction on the efficiency. And the other thing to consider is something more, even more dramatic. Okay, so that's one thing why we want to limit. Okay, that so the curve I will say here, I want to operate only from here to here, for example. Okay, due to efficiency. But there is another thing, another reason, which is something called up thrust and down thrust. Okay, I think I had, let's say, a figure. Maybe it's here. Yeah. So depending on the construction of the pump, okay, you have they're called floating impeller and solid. Okay, but depending on the construction of the pump, usually if you have this floating type pump, the impeller is not fixed to the axis. Okay, it's just it has the ability to move together with the axis. Okay, it has, we will see now, it has something that allows it to, when the axis rotates, it should rotate, but it can go up and down. Okay, if you have too much flow, okay, this will tend to slide and knock with the surface up. Okay, and if you have too much pressure, if you have too much force pulling it up, it's going to start to create a lot of wear in this part. Okay, and eventually it's going to be wear, overheating, and destroy. The light that will have to be replaced if the flow is too high entering into the impeller. If, on the other hand, you have too little flow, then it's going to tend to lay on this support here, and it's going to rotate, creating again a lot of wear and a lot of heat, and then it's also going to have reduced lifetime. So you want to be always operating in a range where the upthrust, you don't enter into upthrust and you don't enter into downthrust. Okay? And I didn't bring it here today again, but if you see, it has two things. These are called washers, and it has a washer on the front and it has a washer on the back. It's an area where you have this, support, this localized support.
Can you just fix it in the middle and then not to move up and down?
That's the other option, but then to install it, you have to be very precise. It takes a lot of time to install it. If you fix it to the axis and you say, well, I will keep it exactly here, it's a kind of it's another type of pump, and it's a more time-consuming operation. Then, if the temperature changes, you have also expansion, thermal expansion. You might have also contact. So it depends. But in this, besides the efficiency issue, in floating type ESPs, this is also a big problem that you have to take into account. Yep.
You can also include some holes at the top of the impeller to reduce that effect.
Include some.
Like tiny holes on top of the impeller in order to reduce that pressure differential, therefore this effect.
Yeah, you have other sort of tricks, but what Juan Manuel is saying is that sometimes you connect. This is not a very good figure to show it, but you have here the high pressure side, okay, and you have here the low pressure side. So you can, if you connect these two sides, somehow you put some leakage between them, then the forces at the top become similar to the forces at the bottom. Okay, but you're losing. Yeah, this is not a very good figure to explain that. But you are because you create a leak, so you are not all the flow that is going here, some part of the flow will go back, which makes it less efficient. Okay, but let's keep that issue outside. What I want to convey here is that you have two limits on the two sides, due to efficiency and due to this mechanical issue. Okay, and the mechanism to fix it, I think I have here. It's interesting. I don't have it here for some reason. Okay, it's a key. So this key allows it to be, rotate together with the axis, but not to, but to be able to move up and down. So at the end, we say, well, our operation, because of that, these two things, okay, efficiency, up thrust, down thrust, we end up with, okay, we have F min, then we have F max, okay, and then we have two lines that will be the up thrust or the maximum flow line, maximum flow, and it's not flow line, but it's maximum flow line. And then you have this down thrust, minimum flow line. Okay, and at the end, that tells you just that your area, actually, your operating area of the ESP, it looks like that. Okay, it's just like nice, I'm not sure if a trapezoidal or something, but that's the where you should be always operating your pump. Remember that the best efficiency, we have a line called the best efficiency line, usually goes someplace like that. That's the best efficiency line. And you want to be operating, as close as possible to that line, because that's where you have the highest efficiency. So let me put here that best efficiency line. And if you, for example, if you have, so for design, okay, if I'm in the design phase, okay, if I haven't selected an ESP yet, okay, let's say I'm in the design phase, I get the rates from the reservoir. Okay, I say I want to produce time 1 Q1, time 2 Q2, and so forth, and that's the exercise you guys are going to work with today. Okay, so I calculate for each one of them. Let's say here I have delta P versus Q, and let's say I have the points will move something like that, right? I calculate the available and the required, and I have 3 points. And I have to find, maybe I go to my catalog, and then I have a pump that looks like that. Then I go and I have another pump which looks like that. So that will mean that I have to change pump, right, from time 1 to 2. Okay, or maybe I have a pump which it's like that. Okay, that is the operational area is big enough to have, to produce to cover all of my points. So that's basically the design, to make it in a simplistic way, the design of these are the values given by God, okay, reservoir engineer, production engineer has to come and they have to say, well, I have to find a pump, one pump, two pumps. If I don't find, I say, well, I didn't find one pump that could produce those rates that you told me. So then we will have to change the pump. Then it will be more expensive in the life of the field. We have to buy a new pump. So then I have to go back to God, and God has to say, well, I can make an adjustment, and I can, let's use not this rate, but let's put a rate something like here, okay, to make your life easy. Not saying that reservoir engineers are God, but they have a big responsibility to, because they are the ones that decide how to use the field. They have also to be sure that that you fulfill the operational restrictions, that rate is actually feasible. Okay, so always remember we are going to talk about that a bit more after Posque, but you have that reservoir engineers finds the best way to produce a field, the best recovery factor, the best cumulative production, the best NPV of the field. But then you have to verify that actually your numbers that you decide they can be produced. Okay, so actually you have a back and forth process. Comes the reservoir engineer says this is the best solution, goes to production engineer says no, it's not going to fly. So you go back and forth, back and forth. You have some fights in between. So okay, so that's an example for okay, different types of pump. What I told you before, that's taken from a paper, actually the work that we are going to make today for the Peregrino field. And you see basically that the envelope can be very different. Okay, this one likes for small rates but big head. This one is for big rate and small head. This is for small and small. You have everything that you. Okay, now, before we have one last thing before we go to our exercise today.
I just want to know,
Yes.
are these pumps like these curves based on uh, like reservoir conditions or surface conditions?
These are for, remember, the rate shown here is always for local conditions. Okay. So this is the rate. If you want to see if your pump works or not, you have to use the rate at local suction conditions. Okay, at the suction of
Bottom
the
hole
pump.
conditions.
Hmm?
Bottom hole conditions.
Bottom hole, or if the pump is a bit too high, then you have to compute up to the suction of the pump. Okay, and in this case, you see, it's for viscosity 1 centipoise. We'll see viscosity has a big effect, and that's also, I hope you are going to manage to make it today. So there are a few more things that we have to say. Okay, the performance of pumps of ESPs is um, eh, affected or is reduced by increased viscosity. Okay, very important. And actually, if you had, again, I'm going to put this plot, you're going to get tired of it. Okay, so if this is for viscosity equal 1 centipoise, that will be for water. Okay, if you use, for example, for 20 or 100 centipoise for a very heavy crude, your curve will be dramatically reduced. Okay, that will be, for example, 100 centipoise. And that will make your operational region, okay, if you remember that I had this nice square, okay, it will also affect every line in that region. Okay, it will affect, maybe that line will be now here, the other line will be here, and this maximum rate will be here, okay, and it might place it in completely some other place that you have. And that's especially important, going back to our emulsion, why I'm talking, this guy is talking about emulsion, because if the water cut, right, the water cut in a heavy oil field or in a water flood project, okay, it's going to initially be 0, and it is going to increase to maybe 90%. Okay, then you're going to pass through the whole range of this emulsion. Okay, when you make that from 0 to 90, okay, you're going to go through this emulsion viscosity versus from 0 to 1, right? And then you're going to have changes in viscosity, and then it's going to be a problem. Okay, then your operational envelope is going to change, and I have to take that into account. Yeah. Okay, so that was one thing. Viscosity is going to affect the performance of my map. The way there is really no bulletproof way to predict that, but we have. Okay, so that's also taken from a paper, how it looks like. And let's see if I have the standard. No, I don't have it. But you actually have to measure to estimate the performance for different viscosity. Okay, you have to make usually measurements, which are very expensive. Has to be done with the manufacturer. They have to test the pump. Or you can also use, here I don't have the name, I always forget. I think it's so it's a standard called the Hydraulic American National Standard, uh, from the Hydraulic Institute. Okay, people that work with pumps, they have been working institute for a long time. And if any of you has the curiosity, that's what we are using here. I'm not using measured data, but basically I'm using this standard. Okay, the last issue was in 2015 and it's called 9.6.7. Okay, but really this sometimes it works, sometimes it doesn't work. So if you are working in a project in the future, you're working with ESPs, be careful that you know exactly how, that they are predicted properly. Okay, now the last, or the one before the last, one thing is the pressure at the suction has to be greater than the bubble point pressure at suction at suction temperature. Okay, because otherwise you will have, remember that when we go on the pump, when we go from the inlet to reach exactly, if we see our impellers, they look something like that. Okay, a bit ugly, but okay, to reach exactly this point, you need to have, the pressure will be reduced. The pressure will go from a high pressure to a low pressure. And if that happens, you might, let's say that this is the pressure of the fluid. Okay, and here you have this axis indicates distance inside the pump. Okay, and here you had, okay, P at the suction. Okay, it's going to go down and then it's going to increase. Okay, and after you go through the first stage, let's say that's the exit of first stage. Okay, then you will have again the same process, going down and increase up, going down and increase up. Okay, but for that first stage is very critical. Let's say that the P suction is exactly the bubble point pressure. Okay, if you go down, then you will have that gas bubbles are going to start coming out of solution. Okay, these gas bubbles, they might do very nasty things on the impeller. Okay, they might accumulate, they might block part of the impeller such that you reduce the passage. They might have cavitation, okay, in which the bubbles, they are in gas, but then afterwards they convert to liquid, and then they heat, they create a very strong hammering force on the wall of these blades. So usually the P suction has to be greater, okay, and we say the P suction has to be greater than a factor times the P at the bubble at the suction temperature. Okay, just a safety, that will be a safety factor. Okay, and the last, okay, that we are going to consider is actually that the power has to be less or equal than the power capacity of the motor. Okay, and remember the power we calculate by of the pump by delta P, the rate in local conditions, okay, divided by the mechanic and the hydraulic efficiency. And we are not talking about volumetric. We are just going to keep it simple in this course. Okay. Any question before we go further? No. So we are going to now after we come back, and I'm going to help you a bit. That's going to be actually your exercise 3. Okay. Remember, if we don't do, oh, that's something interesting to say. Okay, if we don't do exercise, we don't fix, all the blah 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 I'm telling you here in class. Okay, Yeah, so we are going to look at. I had tried to make a model of this field as accurate as possible, and I hope it's very similar to the real field. So that's the Peregrino field. It's a field that is offshore Brazil. I think I have some picture here. Okay, it's Rio de Janeiro just in front. I think it's like 80 kilometers or something from shore. And that particular it's has two platforms where I have producers. Okay, the producers you have here, they are vertical and then deviated, and the let's see here, if you have, the viscosity is actually very very high, so they decided you will have non-economic rates if you just produce by natural depletion. Okay, so they decided to have, that's why you need the platform. Okay, because you have, remember this, what I told you before, wells with ESPs, the lifetime is maybe 6 months. It's very uncertain, but might be from 6 months to 1 month to 2 years in the best case. So you need to make frequent intervention. If you made it a subsea well, then you have to make intervention every 6 months, for example, in the worst case, and then your economy goes to the garbage. Okay, so here you have your wells, and they are producing against a constant pressure, wellhead pressure. Okay, and we have to make our task, and that the file is in actually in my on my website here. It's in the class files. Okay, it's here for all of you to open, and we have that reservoir engineers. Okay, they have said that that's the way we want to produce that well. Okay, they have found the best way, increase recovery factor, etc. That's the way I want to produce it. That's going to be your oil profile, water profile, reservoir pressure, yeah, and the liquid profile with time. So now we say we have gotten from the manufacturer a proposed model, okay, of ESP that I think is here someplace. This Centrileaf 675, okay, and then we have to say, well, with the rates that we got from Reservoir Engineer, we have to calculate that delta P versus the rate, and then we have to plot it on the pump performance map that I have here and see if the point falls inside, and if it fulfills all the operational conditions that I have just described. Okay, so let's take a break, and we come back, and I will give you. This is going to be the second exercise of your exercise set 3. Okay, so I'm going to give you some orientation. What do you have on the Excel sheet? How to solve it, and then the hope is that I will solve it, and you're going to solve it with me. Okay, so let's take a 15 minutes break. Okay, so we have one thing I forgot to mention also. Even maybe you will be faced, with that in the future. There are slightly different designs of impellers that are a bit more initial. We don't want any gas on these machines. Okay, on these ESPs. Gas, they create these accumulations, they create this cavitation, they create a lot of issues, and the efficiency will be significantly reduced. Okay, but if you cannot avoid it, you have some gas that will be liberated, then you have to go for a design which is, you see here how the flow enters basically actually, and then goes almost completely radially. Okay, that gives you a very nice pressure increase per stage. Okay, but it's very bad for gas. If you have gas and you have a liquid, when you have a sudden change of direction, that will tend, the liquid will go on one side and the gas will go on a different side, just because they have different densities. So that will create separation on this machine, and you stop having a very nice mixture, but you have two phases that the machine was not designed for. So if you have has high gas fraction, and high, we were saying 10%, 20%, not much. Okay, then you use this design that gives you less delta P, so you need more stages. Okay, but it's more tolerant for gas. And also remember, the pressure is going to increase, so maybe gas will be driven back to solution after some stages. So maybe the first stages will be like that, and then the other ones, they can be like this. Okay, so keep it in mind. It's like gas tolerant ESP. Okay, so going back to our example, we're going to use real values from a real field called Peregrino in Brazil, offshore Brazil. I hope you know if you haven't been to Brazil, you have the chance to go. Nice place.
When?
I don't know. You have to ask your, the institute to take you to Brazil. So I don't have money, so I cannot take you. But maybe the institute has. I don't know. I think they're going on a trip, right? The Thomas on the first class, they're going on a trip. Okay. So we have the same thing. We have these wells that we have ESPs on them. The production then is taken here. The oil is taken here for processing, and then you use these tankers to offload the production, and you have two platforms. And let's see what else do we have here. Okay, that's how the reservoir looks like. It's tilted. It has oil, and it's heavy oil. We will see now how heavy it is. It's actually quite heavy. And you have water injection, and that's why if you see the profile, okay, you see I didn't plot here the water cut, but actually the water starts to, I initially get no water, but it starts, very sharply after 2.5 years, it starts to increase after the waterfront has reached the producers. Okay, so we are going just to look. I say, please verify. Okay, the manufacturer, they have selected a design, okay, a ESP, and please make, if it you can use it to produce the rates that we want for year 1, 3.3, 6.8, and 12.5. I took 3 points from this plot here. Okay, and we already have, I think I have a completion diagram, but I'm not sure if that's going to be very exciting for you, but just to show that the well is okay. So we are going to make our verification for this year, where you have low to no water cut, 1, 3.3 someplace here, then we have 12.5, it's here, and then the other one was 6 point something, 6.8, 6.8. Okay, so that will be someplace maybe here. Okay, so we have, for these rates, we have reservoir pressure, we have the rates, and we have to verify if the pump, how is it going to operate. That's the completion. I'm going to put it here just for to make it a bit more beautiful, the notes. Okay, so here you have the ESP. You have actually that the annulus is completely sealed, so you have no production, everything. So that's why you have to be sure that you're producing your bottom hole pressure, you don't get any gas. So it should be always above the bubble point. Okay, so this is, you cannot produce anything from the annulus. Yeah, and then you have these two lines that I told you before. Uh, you're injecting also some chemicals. This, they say there that the dispersion was going to be very bad. You will have a very bad emulsion effect. So they say, well, if we inject some chemical, we can try to break that emulsion to make it less severe. Okay, so the peak won't be so severe. But we are not going to look at that, maybe later. But when we talk about optimization, but just don't worry about it. Okay, so let's see what we have here in our Excel sheet, and let's see how do you propose to attack the problem. Okay, what is the first thing, the same thing like with the subsea compressor, what is the first thing we have to make? The pressure upstream the pump and the pressure downstream the pump. Okay, be aware that they might be not exactly in the same place, right? You might have like some distance in between. The suction might be much lower, the discharge might be much higher, but what matters is that the difference in pressure, okay, between the two. Okay, so let's see if we have that information here. Okay, we have that the construction is such due because the well is horizontal and you have to have this kickoff point. Okay, so actually the ESP is not all the way close to the bottom hole, but actually it's much higher. Okay, it's a much smaller TVD because the well starts to deviate, and then you have the kickoff point for the horizontal section. So you cannot put it. The ESP cannot run on a deviated or horizontal section. Okay, you have to have it in a vertical, and that has to do because of the bearings. If you have it vertical, exactly, you have no load on the bearings, on the radial bearings. But if you have it like that, then you have a lot of load. All of the weight of all of these stages, they are on that bearing, and then they get damaged very quickly. Okay, so we say we want to calculate. So first we have the rate, right? Then we go from reservoir pressure and we calculate PWF, right? That we do with IPR equation. Okay, so we have IPR equation. We're going to use exactly the same. The Q, and here I say for total liquid will be J for total liquid times PR minus PWF. We have Q that was given by someone, reservoir engineer. We have J, someone measured for us. We have P, and then we have to calculate PWF. Okay. Then after that, we have the pressure exactly here, and we have to move forward to the suction of the ESP. So now we go from here, again, suction pressure. What equation do we have to use here? The tubing, but it's not the same tubing we have used before. Remember, that's for gas. Okay, so here we have to use that Bernoulli equation that we say H1 equal to H2 plus delta H. Okay, and I have made your life easy, and that's already programmed here. So let's see. You go to the BBA module. I think you go to single phase hydraulic. Okay, and then you have P in has all the data that you need. Okay, you specify the rate, internal diameter, density, viscosity, the length. Theta is the angle from the horizontal, P out, and the roughness of the pipe. Okay, which are you going to use, P in or P out? P out. Okay, we have the inlet pressure is the of that conduit. Okay, now we are looking at this part here of pipe, okay, which is flowing the casing. So we are going, this will be my P in, and I want to calculate P out, P at the suction of the, okay, so let me take a screenshot of that. P out, that's the equation we're going to use. Okay, but please note something important here. So we have that equation needs the rate. Do we have the rate? Which rate is that? The local rate, right? So that's a problem. But here we're going to make an assumption. So you have to assume, if not, it will be to remember, we should do it step by step. We should discretize it and make it in steps. But we are going to assume that BO is very close to 1. Okay, and also B water is very close to 1. That's one assumption we're going to make just to make our life easy. You will have to, and another exercise you have later, you will have to change that assumption. You will have actually to make the calculation. So that means that Q oil will be equal to Q oil at a given pressure and temperature, and Q water is actually equal to Q water at pressure and temperature. And that means that the water cut, which was originally this guy, is going to be exactly the same as the water fraction, which is this guy. Okay? Only for this exercise, to make your life easy and my life also easy. Okay? When correcting. Yeah, so you need density. How do I calculate that density? If you remember, we were doing last class, density of the mixture is it like that? times density of the oil. And I have programmed that equation for you also, so you don't have to. So that's called this average property function. Where is it? Here. You can use that average property. You give the property of the oil, property of the water, and the water cut, and it will calculate the density or the average property. What about length? Which length should I use? H1, right? And diameter 1, roughness, it's here, okay? And the angle, theta, the angle theta is the angle from the horizontal. If you have P in, P out, and that will be theta, okay? So in our case, we are assuming vertical well, so theta is equal to 90. What else? Now comes the big challenge, okay? This guy here, the viscosity. Remember that the viscosity we said has this behavior 0 to 1. Okay? And for that, you see here I have provided the Richardson exponent, okay, for both for the water and for the oil. Okay, that means that you will have to use that equation for this side, mu oil times E to C oil alpha of the water. Is it 1 minus? Sure, I don't remember. Okay, you have to check on your notes. Okay, and this side we're going to use mu of water times E C water 1 minus alpha water. And is it like that or the opposite? Yeah, like that? Okay. And that equation is also programmed for you. So it's, let's see, should be here in emulsion. Okay. You need the viscosity of the oil, viscosity of the water, this volume fraction, that is the water cut, the exponents, and the cutoff. Okay, the cutoff is exactly this number. So here this inversion point happens at 0.6. Okay, so here it will be 0.6. So if here you have an if inside that function, okay, if I'm above the cutoff, I have to use one expression. If I'm below the cutoff, I have to use another expression. Clear? Yep. Okay, so that's the expression I'm going to use for viscosity. And then you see, well, we can calculate very successfully the pressure at the suction of the pipe. What is the next step? I have to calculate the pressure required, right, at the discharge of the pump to calculate the delta P of the pump. And I said, well, the wellhead pressure is kept somehow constant at 7 bar, okay? And then I have to go from here all the way down, okay, to calculate the discharge pressure. And then I'm going to use exactly the same equation, exactly the same input, okay, exactly the same viscosity, no change. Then I can calculate the delta P. Then to make the plot on my, to put the point on the pump diagram, okay, I need the head, so I calculate the head, delta H divided by rho G. Okay, and then I see if the point falls inside the head, inside the performance map. That clear? Yes. Huh? Delta P. Delta P is, what is the delta P of the pump? P discharge, we want to make it positive, minus P suction. Okay. Delta P, yeah, that's correct. Delta P. Okay. Yes. So, do you want? Should we make a kind of a group work? You work a bit on that, or you want that I will do it here for you? because I'm afraid you're going to fall asleep. Okay, if I do it here in groups, yeah. So let's say put 20 minutes. You gather together in group and you try to at least to try to populate, all the things that I told you now. And then we go to this efficiency, and first we go to the map, and then we go to the power and the efficiency.